Hey guys, Spencer here in the Kinetic Precision shop. Today we're going to be taking a look at lathe cutoff tools. And I've had a love-hate relationship with lathe cutoff tools over the years, and I wanted to share with you what I have learned and the latest addition to the lineup of cutoff tools in the shop. So this is an ISCAR, I think they call it an F-tang. But it's a very interesting tool, uses a very interesting shaped insert. This came highly recommended by some of our folks on Instagram. So I want to try that. I bought a kit which consisted of insertion tool, the blade, 10 inserts, and that came in pretty quickly from my tool distributor. Less quickly was getting the Dorian tool holder. So this is a Dorian tool holder for my V35TC tool post on the TL-1, and this is going to hold the blade. This also has the capability of squirting coolant into the right place, which I really don't use very much, although I am plumbed up for it. So I don't think we're going to get around to playing with that. I'll bring you in for some detailed video on putting together the new tool holder and getting it on the TL-1, and maybe we'll get a chance to cut some things with the new blade. Here is the this is the thing that started this whole project. This is a bar of titanium, and a friend of mine in the Instagram community asked me if I can slice it up into 3/16 slices. And I said I would, and it was a while ago. First I tried saw cutting it. We talked about this on the PFG Live. This is 2 inches in diameter, and this is a titanium which I haven't quite identified. There is a marking here, but I can't read it. And it was a complete disaster. So it probably cost me a saw blade. So I wanted to go to a cutoff tool. The cutoff tools I have, we're not going to do a 2-inch diameter, and that was one of the big things. So this tool is capable of a 2-inch diameter. It is a 3mm wide tool with this very nice insert. And let's see how we do. Stick around. Okay, let me explain to you what the problem we're trying to solve here is. We need to be able to cut 2-inch diameter work, but this is titanium, which means it's going to be really kind of tough to cut. So we needed something pretty stiff. The tools that we had in the shop are 3. One is an aluminum block that I made a long time ago to hold, let's see, what are these? These are 1/2-inch blades, I think. Yeah, they're under a half, but basically roughly 1/2-inch blades. This is an 062 wide blade. It's high-speed steel. So it has limited limited stiffness. Really good for delicate jobs where I could put a custom grind on the cutoff tool. But isn't going to do the job. This would be destroyed in the titanium. Also, this was originally made for a smaller lathe, and you can see that I have a tool bit as a little cheater spacer. So not exactly the stiffest tool in the drawer, not going to work. The second tool, which has done most of the parting off in the shop in the last couple of years, is this Coro cut. I'll give you a close-up of this. Coro cut by Sandvik with a nice, and I mean nice, carbide insert. And this thing will cut absolutely anything. The trouble is, it is limited to about just over a 1-inch depth of cut, which means 1-inch diameter work, and that's really not going to do the job. The third tool we have is the same exact holder, except I have a radius tool. Let's see if we can get that. There you go. A radius tool, and that's been a really nice tool for certain projects on the lathe. So those are the tools we have. Those are the tools that aren't going to do the job. That's why we brought in this this ISCAR, and here's its tool holder. So this guy is going to sit just like so and extend out plenty enough for us to do our job. This is the clamp that goes on top to hold it down, and we're going to put that all together. This is a pretty clever system, and these inserts, they call them F-tangs because they look like the letter F, come with a pretty neat tool. So one of these pins goes in the hole, and this pushes down on the insert to install it. The same tool would insert under the carbide insert and pry it out. So there's your insertion and removal tool, and there's your blade. And of course the blade has two ends. In case you butcher one up, you're still able to use the other side. So let's put this all together. I'm pretty sure that these are metric, but yeah, these are metric. So let's see if we can't figure out. No, 5mm it looks like. Yep. So one thing I have not figured out yet, and maybe somebody can help me with this, is that there are two set screws here to limit the depth that I can put this in at, and I don't really understand how they're used. So we'll have to figure that out. These Dorians, this particular series, has a input for coolant and then a hole to squirt coolant right on the blade, which is pretty interesting. I don't know if we're going to end up using that, although we are equipped for that. All right, so this is the correct orientation. Here we go. Interesting. So what's interesting is that if I push this, this has a wedge. Take a look at the shape here. Okay. This has a wedge that pushes down on the blade, and if I just literally put finger pressure on this wedge, that blade is locked. If I take my finger pressure off, it stays locked. So these angles were figured out pretty carefully. Again, I could slide this guy back and forth, but as soon as I put finger pressure down on this clamp, that thing is locked. I am very happy about that. So let's put out one. Let's see, we want to be able to cut two. So let's put out about 1 1/4. Yeah, that's about 1.2 inches stick out. And that ought to happily go through that work. So we'll leave that at 1 1/4 and drop these guys in. I don't think we're going to have to put in much gronkage here. So I left the tail one loose, okay, and I'm putting finger pressure on these guys. And literally that was just a little bit of pressure. And if we look in the back end, we can see the geometry there. Okay. So let's give it a little gronkage. I'm going to start in the center, to the front, to the back, front, center, front, center. I'm concentrating here because I've got solid support here, solid support here. This guy is starting to get into the area where it's open, and that's got me nervous. In fact, I'm going to loosen that guy up. I didn't have to, he stayed loose. So that's it. I didn't go crazy wonking these guys down. I don't think it's necessary. But that's looking good. Now, one final check on the stick out. Yeah, just shy. Just shy of 1.2. So this is 1.188 easily. So this is 1 3/16. I think we're almost there. The other thing I have to do is I have to tighten the height adjustment stud, not 5 millimeters, 4.5 millimeters. This guy I'm going to give a really good gronk to, and that's in there. So this guy's ready to do a height adjustment. And I think we got it. Let's head over to the lathe. Okay, we're over here at the Haas TL-1. This is the Victor V35 TC tool holder. And this is an equivalent to a CXA size, Charlie X-ray Alpha. We haven't set the tool height of this thing at all yet. Let's do a test cut in something simple. This is a piece of pre-hard that I use. I made a thread gauge out of it a while ago, and we're just going to slice. We're just going to slice off the end of it. So we have a little nub on this particular piece, which we're going to use to approximately set our tool height. I got an A-bomb sized wrench here. I loosened up the tool post again. Oop, it moved. It's probably good enough. That looks really good. I think we're going to go with that. Okay, so 4 thousandths to 10 thousandths inches per rev is the recommended. So we're going to go to 4 thousandths because we're wimps. Max RPM is 1,000, but now we could feed it a surface feet per minute, and the book says 270 to 590, so we'll go to 275. How's that? So now we've got tool 12, work offset 54, 0 is the end of the part. It's a 1.1245 outside diameter, 20 thousandths diameter to cut 2. Make me a 50 thousandths thick disc. The tool width is 3 millimeters. Give me 4 thousandths per rev. Max 1,000 RPM. Give me a surface feet per minute of 275. I don't know. This looks pretty good. Let's get it set up. I would say that's a win. All right, let's try another one. This time we're going to go cut to a diameter of 0. That seemed to work pretty good. So I'm just going to make that modification here. Diameter to cut 0.0. We're going to crank up the surface feet per minute. We're going to go to 300 because it's easy to remember. And leave the feed per rev at 4 and let it rip. I still have the rapid set at 5%. Just manually turned on the coolant. Beautiful. Awesome job. All right, let's stop here and we'll set back up for the next type of metal. Well, after some success with our cutoff tool, I realized I had a problem. The problem is that I forgot that the through hole on this chuck is too small for the 2-inch part. So what I did was I chucked it up and I put a center hole on the other end, and I put a live center in the part. And my initial plan was to cut the part most of the way through and then maybe finish it or twist it or something, just so I wouldn't get into the situation where the part would bind the tool, which would be a disaster. Well, I think I found a way out of this by remembering I have an 8-inch 3-jaw chuck, which will have a 2-inch hole, and I think I want to go that way. So I'm going to pull the bar out, and I'm going to pull the chuck off, and I'm going to double check to make sure my spindle tube is big enough. And if it is, I'm going to put the 3-jaw 8-inch chuck on here and make this a much simpler problem. Stick around. So I know that the outside portion of the chuck is not necessarily precise, but I'm just going to give it a quick check. I am seeing 1/1000th of an inch. So let's put a pin in, and we'll measure a pin and see what that looks like. So here's a hardened pin. Let's see what this does. We'll tighten it up with the pinion marked as 0, which I don't have a pinion marked as 0, so we'll just tighten it up. Just a little snug, not crazy. Let's see what we got. Well, I would call that about 2/10, 2 to 3/10. So I'm not even going to argue. I'll take it. Who am I to argue? Okay. That was reasonably painless. Let us proceed. This chuck feels a little like it wants some cleaning. Oh, look at that. That makes me very happy. I thought we were going to have to get mighty janky with this thing, but apparently not. Okay, so what we're going to do is we're going to find the end, we'll touch off the end. The diameter is good. We trust the tool because we just indexed it on the previous work. So I think we're going to touch off and try a slice. First thing I'm going to do is make sure that we actually have the depth we think we have. No problem. All right, we're on tool number 12, offset 54. We're going to start at 0, outside diameter. We have not set the outside diameter. Believe it or not, it's 2.002. All right, so we're going to part off. First thing we're going to do is clean this thing up. So we're going to tell it we want a 250 thousandths part. And all the other parameters are the same. 5% rapids. We'll check our coolant. Coolant looks good. And we're ready to go. Well, that was awesome. So we didn't break a chip. That's lesson number 1. But we survived. So we have a long string of titanium. But look at that finish. I got to tell you, I don't know if it'll come out. Let's see if I could focus it here. The finish on that cut is just astounding. I think we have a winner. I think we did it. All right, I'm going to clean up and I'll bring you back. Well, I would call this a complete success. Now, we know that we have to do something about the rat's nest. And the TL-1 has a parting cycle called part off with peck. So I think we're going to peck it, and that will force a chip break. And I think we'll avoid the rat's nest. However, the result of the cut is absolutely glorious. The funny thing is, it was so close to the saw cut that I guess when the part came off, when it finally broke off, it pinched this little lip. But the finish on the saw cut is spectacular, like really spectacular. It broke off kind of the same as before. It has about a 70-80 thousandths diameter when it decided to break, which is interesting. I'll double check my tool height after this. But the tool didn't hesitate, it didn't whine, it didn't shatter, it didn't do anything. So I'm very encouraged. So I'm ready to go ahead and start making these slices for my buddy. And he asked for 3/16 inch slices, so that's what we're going to go for. So first we're going to check tool height, and then we'll get ready to start slicing the titanium salami. Okay, so we're going to double check the tool height, and the nice thing is we've got a nice pip in the middle. It actually looks really good, and what it's telling me is that the tool height is mighty close. So let's just find out what we can learn here. Let's see. How's that looking for you? Yeah, I'd like to get you in there closer. I'll take some stills as we get there. All right, so we're on fine movements now. Boy, that's pretty good. I would say that's as close as we dare try to get. I don't think we're going to do much better than that. So I think we're going to leave it alone. How's that for a decision? Okay, we're going to try a cut now where we increased the feed per rev from 4 thousandths to 4.5 thousandths. And we bumped up the SFM from 300 to 350. Let's see if we break a chip, not a tool. Yeah, let's go. That would be a nope. So I blew it. New tool, exciting new toy. I broke it. So I had a pretty nice failure. And I've always said that the way to succeed is by failing. So let's take a look at what happened. First thing I did is I took some 4140. This isn't the bar, but it's the same material. Some 4142 pre-hard Rockwell C22, and ran it at 4 thousandths feed per rev and 300 surface feet per minute. Was beautiful, and I mean gorgeous. So I swapped in the titanium, and I went with the exact same recipe. And this is my bag of chips, okay? And except for not breaking a chip, it performed beautifully, or so I thought. And then I sought a way to break the chip. Now I got steel think, right? So I upped my feed a little bit, and I upped my surface feet per minute a little bit, and that was the end. I broke the insert, crashed the tool into the part, destroyed the holder, right? Here it is, and learned something. So I have another end to the holder. It's double-ended, so I'm going to reload. But what happened was I got on the phone with ISCAR, okay? I called up ISCAR, and I got a super nice guy on the phone. His name's Tony Green. Tony was awesome. They're down in Texas. And he explained to me what I did wrong. And what I did wrong is that the surface feet per minute was way too high for titanium at the get-go. So 300 was already out of the range, and I was lucky. So he gave me 100 to 195 surface feet per minute for titanium with coolant. And he taught me something else that was really interesting. He says that the tool should be set anywhere from dead on center line to 3% of the width higher than center line. So I have a 3 millimeter wide tool that came out to 0.0036 inches above center line. So anywhere from 0 to 0.0036 was the recommended setting on the tool. I found that pretty interesting. I was set to approximately dead on. So that was all a great lesson. I'm not hiding the failure. I failed, and I learned a lot. So what I'm going to do is I'm going to load up that tool again, new insert, the other side, go back to the titanium. I'm going to drop my surface feet per minute into the range he gave me, 100 to 195. Probably I'll do 110 surface feet per minute. Oh, the other thing he said is make sure that your RPM limit, because on the lathe the RPM will go up as your part gets smaller. He says make sure it's as high as you can put it, so that you don't give up on that surface feet per minute for as long as possible. So those are my goals. That's what I'm going to do. And I've licked my wounds. I had the crash. I grabbed my tea. I got in the truck, and I drove to the post office to make a delivery, or to put something in the mail. And now I'm going back to it. So stay tuned. We'll let you know what happens. Okay, so we cleaned up the buggered up end. So we're going to use the second end, and I'm going to show you how this works. So these are the inserts. Okay. So you put the insert in the slot, push down a little bit, then you get out the tool. It's pretty neat. And you push down. Boom, that's it. Ready to go. So we're shooting for about 1.25 like we did before. Double check. Yep. I'm only tightening the first two screws. This set screw is used to release the wedge. So when you go to loosen them, the wedge is going to stick, just like a taper. So you tighten this screw and it jacks the bar up. And these we're leaving alone. These are going to stay loose. Okay, all of these are loose. We're tightening these. Front one first, back one second. I'm sure there's a torque spec, but that's basically it. This guy is ready to cut. So when we had the mishap, the tool post got bumped. So we're going to reset the tool post. I just have a bar, flat bar from over on the grinder. I'm just going to use that to set it. Hold it. Give it a little tighten. Give it a little more tighten. And that looks good. One more for good luck. Now we'll check it. And if we don't like it, we'll make an adjustment. Okay, we've touched off the tool in Z and X. We've aligned our coolant nozzle again, and we've set up our tool post so it's square. So we're back in business. We're going to dial in a new set of parameters. Well, I'd say that's a pretty good recovery. We heard some sounds in there, so let's investigate. It looks really good. It's not as nice as the first time we cut it, but it cut it. Did what it was supposed to do. And I'll also note that It was set for 0.25 diameter, and that looks a little bigger. So it's still falling off before it achieves the programmed diameter. So I may change that programmed diameter to 30 thousandths. Let's investigate more. The chips are good. They're shiny. They're not darkened, so they don't look heat affected. I like it. We'll save those chips for documentary purposes. Tool looks good. Yeah. I don't think anything was bad here. So why don't we, we're going to move our reference point over and make another cut. So this is going to be 120 surface feet per minute. Still 4 thousandths per rev. And our part length is going to be 0.190. Our max RPM is set to 2,000, which is the max for this lathe. I just opened the valve a little bit more on the coolant. This sounds a lot better. That went really well. I liked it a lot better than the 110 surface feet per minute. We'll examine it and decide if we want to keep it. Oh yeah, we want to keep it. That came out great. Much better than the 110. I think we have a recipe. We're ready to go. So all I'm going to do is I'm just going to put my offset in the control, and it should be good to go. We're still not breaking a chip. That's just life in the big city. We're going to keep the recipe we've got. Sorry you have to look through the plexiglass, but we're using all the coolant all the time. It's almost like we know what we're doing. Well, that's pretty nice. I'm not changing anything. Rinse and repeat. So the one thing I am doing here is making sure I'm getting the rat's nest out of the way. Of course, I'm also looking for my part. There it is. We'll deal with the nub later. So the part is ending up just laying on the on the cross slide, which I think is hysterical. So here we're seeing something interesting. So I went handheld. There is a rub mark on the holder, and that's interesting. It's obviously not hurting us. And I have a funny feeling it may have happened in the slower cut, but not in these cuts. I'm not sure. It actually feels raised, like we're depositing material. So I'm going to investigate this a little bit before we continue. Okay, we've extended the material. We've re-indicated the tool. We have made a slight, tiny adjustment in the angle of the tool. We should be good to go. Right now the spindle load is 42–43%. The X load is 26% and the Z load is 11%. So the the parts are back to landing right on the cross slide, which is really nice. Okay, that sounded a little juicy. I don't know why. Maybe we're getting dull. Could be. Yeah, I didn't like the sound of the ending. So I think we're going to check the tool height. Yeah. Finish is awesome. So when I was talking to the gentleman at ISCAR, he said on center or 3% of the tool width above center. That is looking much better. That's way better. I have a feeling that our maybe our stud was a little loose, which, you know, I've been warned of that sort of problem before. All right, let's see what's going on. Nope, didn't like that at all. That sounded very rough. Well, the insert looks just fine, so I don't exactly know what's going on. We'll figure it out. It could be something as silly as the insert is just getting dull. Yeah, I'm going to vote for insert getting dull. We've cut 20 parts so far, 20 good parts, and it's possible that we're wearing that insert out. After all, it is titanium. And the question is, how far do we push it? Let's double check the height. Boy, that height looks good. Yeah, I don't think it's the height. I think we're going to take a break. And the break we took. So during this time, I had a chance to examine the tool. It did a good job. It did a great job. We were using it a little bit out of its spec. It's originally designed for steel. And when I talked to ISCAR, they said that if they knew I was doing titanium, they would have given me something a little more optimal. However, they like this one, and they think it's a good general purpose tool. So what I paid for that was tool life. We got through 20 of the discs, and the tool did a great job. I'm looking forward to using this tool more. But let's take a look at what happens at the end at the end of the job and why my ears picked up what they picked up. So here you're seeing the tool in its pristine form. There's a shot of the bottom, which is the sort of the seating, locking, locating features. And here's the tool after 20 discs were cut. It doesn't look too bad, but if you look really carefully at the cutting edge at the top left, you'll see it is in fact chipped. And this is what we picked up with our ears, and it was pretty obvious. So we'll take a look at both sides. And here's the chip in its glory. So this makes a lot of sense. This is what caused the sound. This is what caused the finish. But it was still going like a trooper. We did finish it. The right-hand side was better. And you could make the argument that, hey, maybe there's some sort of alignment thing going on. But I think we were just operating out of the specifications for this particular chip. I mean, for this particular insert. So I was happy. It was a good project. Thanks for coming along for the ride. A lot to be learned in cutting titanium. If you look at the leading edge, it looks like it was pretty well behaved. So I can't complain. I bet you this tool does just gangbusters in steel and aluminum and other more normal materials. So thanks for being there. If you want to support the channel, go pick up some PFG stones at pfg.gg. Otherwise, have a great day.